This is Richard Ignis in the Department of Physics and Astronomy at East Tennessee State University. Today we're going to talk about how to travel about in the solar system. This is interplanetary travel within the solar system. There are many ways to accomplish that. You just need enough rocket fuel to do it. But if you want to make use of the least amount of energy to get from one place to the other, you're going to want to make use of something called the Hohmann transfer orbit. The Hohmann transfer orbit takes advantage of the sun's gravity to move a satellite from one planet to another. And in that fashion, it becomes the minimum energy orbit for interplanetary travel within the solar system. Fuel is still needed. You have to get off the surface of the planet where you're starting. And once you arrive at the planet, which is your destination, you also have to make use of fuel in order to enter into an orbit around that world, or perhaps even to land on it. But the Hohmann transfer orbit is one in which you simply get into the orbit and you exit the orbit, but the sun does all the work in between. And it turns out that it makes use of Kepler's laws then. It's just another body orbiting the solar system. So what we're going to do is we're going to look at some examples, and to make life simple, we're going to deal with circular orbits of planets. But the transfer orbit is an ellipse. So let's get a picture. Imagine that we have the orbit for a planet. Let's just say it's the Earth. We're going around the sun. And we want to go from the Earth's orbit to some outer orbit. Draw a big circle for that. The way in which we're going to do this is the ellipse that we're going to have involves starting at the inner orbit, ending at the outer orbit. We'll call this number 1 for where we start. Number 2 is where we end. And to bridge between these orbits, we're going to travel along an ellipse, which is going to be the transfer orbit. So T stands for transfer. Now the idea here is that the radius of the inner orbit is R1. That's this distance here. The outer orbit, also a circle, has a radius R2. But the sum of these two distances is in fact the major axis of the transfer orbit, major axis of an ellipse. Now we use the letter A for semi-major axis. So what that means is that this distance here is twice AT for the semi-major axis of the transfer orbit. And that distance is equal to the sum of R1 plus R2. Let's get another sheet. So what we have is that twice the semi-major axis of the transfer orbit is equal to the sum of the radii for whatever the inner orbit is and whatever the outer orbit. By the way, it doesn't matter where you're starting. You may start at the outer one, you may start at the inner one, but anyway, it's the sum of those radii. That means the transfer orbit is equal to 1/2 R1 plus R2. That makes the semi-major axis of the transfer orbit the average of the radii for the inner and outer orbits. From Kepler's third law, P squared equals AQ. Now, this of course requires that the semi-major axis is in astronomical units and that the period is in years, and that we're talking about orbits around the sun. So if you tell me where we start and where we end, or vice versa, I can get the semi-major axis for the transfer orbit, I can cube it, then I can get the period. However, the period here is the time all the way around the orbit. In other words, from the inner orbit to the outer and back again. What we want is the travel time between planetary orbits. So that time will be half of the period, as it turns out. Then the shape of the ellipse, which is called the eccentricity will simply be whatever it takes in order to match or bridge the gap between these two orbits. So we're going to do an example here, but I just want to make one quick comment. Let me draw that picture again. One of the challenges with transfer orbits is that we're dealing with moving targets. Okay, so maybe this is the ellipse from the inner to the outer. Number 2, number 1, this is the transfer orbit. You launch when planet number 1 is at this position, and you arrive when planet number 2 is actually on the opposite side of the sun from where you launched for the Hohmann orbit. But when you launch, this planet's here, that planet isn't sitting still. This planet is somewhere over here, moving along, while the satellite moves from the inner to the outer. The inner planet is going round and round, the outer planet is catching up. So you definitely want this to be pretty accurate. The timing has to be just right, because you're basically aiming for, you're launching off of something that's moving, and you're aiming for something that is also moving. Okay, let's go ahead and do an example. Suppose we're going to go from the Earth to Neptune. The radius for the inner orbit is, for the Earth, 1 astronomical unit by definition. For Neptune, it turns out it's about 30 astronomical units. Well, this makes the transfer orbit, the semi-major axis for the transfer orbit, is equal to the average of those two values, so it's 30 plus 1. Half of 31 is 15.5. Now this 15.5 is in astronomical units, because these weren't astronomical units. The period then for the transfer orbit, p squared, is equal to a cubed, which is 15.5 in this case. We're going to cube it, see what we get here. So my calculator happens to have a cube button. I put in 15.5, and I have to hit shift, and there's my cube right here, and I'm going to get 3,723.875. Well, that's about 3724 if I just kind of round up a little bit. Not all calculators will have the cube or cube root functions on them. Almost all calculators have squares and square roots, but maybe not cube and cube root. If you don't have that, you may have an x to the y button. In that case, you can put 15.5, you hit x to the y, that takes something to a power. You can put in 3, hit that button again, or the equal sign. I'm going to hit the equal sign, get the same number. So 3724. We don't need those extra digits. Well, the period for the transfer orbit is then the square root of 3724. I calculate back again. 724. Square root is here with a shift. I get 61. This number, 61, is in years. But as I said, that's the round trip time. That's the full orbital period. The time it takes to get around the orbit one full time. The time it takes to get from the inner to the outer is what I'm going to call the transit time. That's just half the period. And half of 61 is 30.5 years. Now it's important to note, this is half the trip going out and half the trip coming back. So actually it wouldn't matter if we started at Neptune and went to the Earth, the transfer orbit would also be 30.5 years. It doesn't really matter whether you're going out or whether you're dropping in between two different kinds of orbits. So all examples of transfer orbits basically work like this. You have to be told what the two planetary orbits are, the radii of those circles. You can then get the semi-major axis value for them. You can figure out the period from Kepler's third law. Then when you take half that value, you get the transit time from one to the next. This is the same amount of time it also takes to come back. By the way, it's worth pointing out what are the periods of the individual planetary orbits. Well, we know in this case for the Earth, number one, p squared equals a cubed. We have 1 AU cubed. Then we're going to take the square root. That's going to be 1 year. Of course, the Earth takes 1 year to get around the Sun. In the case of Neptune, what we have is 30 cubed. We're going to take square root of that. And the number we get for Neptune, 30 cubed, square root, 164 years. So even the full orbit here for the transfer orbit at 61 years is in between these values, but it's definitely not the average. Right? Where the average is not in the periods, the average is in the distances. So that's how you calculate the orbit semi-major axis and the time that it takes to get between orbits on a Hohmann transfer orbit.